For as long as humans have studied the planets of our solar system, Jupiter has stood out as a world of extremes. It is the largest planet by far, so massive that it outweighs all the other planets combined. Its storms are larger than Earth. Its magnetic field is the strongest of any planet, and its presence shapes the orbits, the stability, and even the long-term evolution of the solar system. With a world this enormous, a natural question arises. Why didn't Jupiter become a star? Why didn't the giant of our planetary family ignite into a glowing sphere of nuclear fusion like the Sun? At first glance, it seems like Jupiter should have all the right ingredients. After all, it is made mostly of hydrogen and helium, the very same elements that make up the Sun. Its atmosphere resembles a scaled-down version of a stellar atmosphere. It has layers of metallic hydrogen, enormous pressure at its core, and swirling bands of storms powered by internal heat. And yet, for all of Jupiter's power and immense scale, it never crossed the threshold required to ignite into a star. Understanding why requires us to look into the physics of star formation, the importance of mass, and the extraordinary pressures needed to trigger nuclear fusion. The formation of a star begins when an enormous cloud of hydrogen collapses under its own gravity. As the gas compresses, it heats up. When the core becomes hot and dense enough, reaching millions of degrees, hydrogen nuclei begin to fuse, releasing energy and creating a self-sustaining nuclear furnace. This is the defining feature of a star. Without nuclear fusion, a celestial object, no matter how large, remains a planet or a failed star. Jupiter, like a star, formed from primordial gas, but unlike the Sun, it did not accumulate enough mass to begin the fusion process. Its mass is only about 1,000th of the Sun's, and this difference is everything. For fusion to start, a body needs at least 70 to 80 times the mass of Jupiter. Only then would the pressure and temperature at its core become high enough for hydrogen atoms to overcome their natural repulsion and fuse together. Jupiter fell short of this requirement by a vast margin. It was enormous by planetary standards, but nowhere close to what a star demands. Even if Jupiter had somehow accumulated more material in its early formation, the solar system itself may have prevented it from going any further. The young Sun dominated gravitationally, pulling most of the available hydrogen into itself. Jupiter, forming later, had access only to leftover material from the protoplanetary disk. That supply was simply insufficient to cross the critical mass threshold. Jupiter's growth eventually stalled, leaving it as the largest planet, but far from stellar status. Still, Jupiter did come close enough for a different kind of fusion to be possible: deuterium fusion. Deuterium, a heavier isotope of hydrogen, requires less pressure and temperature to fuse. Brown dwarfs, objects larger than Jupiter but smaller than stars, are capable of burning deuterium in their cores. But even this process requires about 13 times Jupiter's mass. Jupiter is not even halfway there. The giant planet remains firmly below the minimum mass needed for any form of sustained fusion. Another key factor preventing Jupiter from becoming a star lies in its internal structure. Although Jupiter's core is under immense pressure, tens of millions of atmospheres, it is still far from the number required for hydrogen fusion. Stars reach core temperatures of millions of degrees. Jupiter reaches only tens of thousands. It radiates heat, but that heat comes from gravitational compression and leftover heat from its formation, not from nuclear fusion. Everything about Jupiter, from its temperature to its density, places it in a category clearly distinct from even the smallest stars. Its atmosphere also reveals this limitation. While stars have intense thermal gradients and emit radiation across the electromagnetic spectrum, Jupiter emits only infrared heat and reflects sunlight. Its glow, faint though it may be, is not generated by nuclear reactions, but by internal cooling. Jupiter is warm inside, but not hot enough, not dense enough, and not energized enough to ignite the fusion reactions that define a star. Yet Jupiter plays a vital role in the solar system even without shining. Its gravity shapes the asteroid belt, protects the inner planets from dangerous comets, and stabilizes the orbits of countless bodies. Without Jupiter, Earth might have experienced a far more chaotic bombardment of asteroids throughout its history. Jupiter is not a star, but it acts almost like a guardian giant, a stabilizing force that influences the fate of planets, moons, and smaller bodies throughout the solar system. Its massive size also influences its atmospheric dynamics. The bands and storms we see across its surface are driven by internal heat that Jupiter slowly leaks into space. This internal warmth is a faint echo of what a star might produce, but not enough to trigger fusion. The famous Great Red Spot, a storm that has raged for centuries, is powered by the energy trapped deep inside the planet. But none of these processes bring Jupiter any closer to becoming a sun. They're planetary phenomena, not stellar ones. When we compare Jupiter to a real star, the differences become clear. A star shines because the enormous gravitational pressure at its core forces hydrogen nuclei to fuse, creating helium and releasing immense energy. This energy pushes outward, balancing gravity and creating a stable, shining body. Jupiter never achieved this balance. It is massive, but not massive enough to collapse into a fusion-driven equilibrium. It remained a planet, a giant one, but a planet nonetheless. This raises another interesting question. What if Jupiter had become a star? The consequences would have been enormous. The solar system might have become a binary star system, with Earth orbiting two suns. The gravitational balance of planets would have shifted dramatically. Some worlds might never have formed. Others might have been flung into interstellar space. Jupiter's failure to become a star may have been essential for the solar system to evolve into the stable, life-supporting environment we know today. In a way, Jupiter is a bridge between planets and stars, a giant that contains the raw materials of a star but lacks the mass to ignite. It reminds us that size alone doesn't determine destiny. It also highlights the delicate conditions required for stars to form. Only through immense force and staggering pressure can nuclear fusion begin. Jupiter never reached those extremes. It remains a silent giant, reflecting the light of the sun rather than producing its own. Understanding Jupiter's limitations gives us insight into the architecture of planetary systems, the physics of nuclear fusion, and the history of our own cosmic neighborhood. Jupiter did not become a star because the odds were stacked against it from the beginning. It lacked the mass, the pressure, and the temperature required for nuclear ignition. It grew large, but not nearly large enough. And in that limitation, the entire solar system found its stability. If you enjoyed this clear and deep scientific breakdown, don't forget to like the video, share it with others, and subscribe to Wiseuse for more documentary-style explanations of the universe.